Greetings, fellow science fair winners and other technical hobbyists. Thank you for joining us once again and welcome to another video feature. Today we're going to do a little featurette on solar panels, and specifically a small battery charger type panel that you can pick up online or at Harbor Freight on the shelf. These here are relatively not dangerous as long as you don't break them and cut yourself on the glass or something like that. So this is something that you can try at home. Well, here we go. The Harbor Freight 1.5 watt solar battery charger. Compensates for small steady battery drains, plugs into a 12-volt cigarette lighter, panel mounts easily to windshield or dash, and includes suction feet for mounting. Well, let's go ahead and get this little guy out of here and see what it's all about. Given that I paid only about $12 with the standard Harbor Freight 20% off coupon, I doubt there's going to be much to say for efficiency on this one. And given that we're only 5 watts, that doesn't suggest that we have a very modern technology here. Let's see if the manual says anything about it, or if I have to go by the information I found online about this. Installation precautions, battery precautions, service precautions, wiring, cleaning, adjustment. Yeah, no. Okay. Let's just go into the information I found online about this. Harbor Freight advertises this as being an amorphous thin film silicon solar panel. Well, amorphous thin film means that this is not an ordered crystalline structure. Instead, it's just the silicon thin film probably bonded onto the back of the glass panel here. Basically, this is a very large version of the classic calculator solar panel. I think I see a little bit of defects down in there, so I don't know what that's going to do for us. But the worst thing we can do is plug it in and test it. Okay, red to red, black to black, and there you go. This one is generating about almost 1.5 volts sitting here under the shop light. Alright, now let's try something that's ridiculous and just plain funny. Here are these little Harbor Freight lights that they're currently giving away free with the coupon. I've taken apart a few of these in order to use the cob LEDs out of them, and it's kind of fascinating. Almost none of these are built the same way. I mean, you can see some variation just right here. This one here's kind of got that mottled pattern on the reflector, whereas this one's just straight up reflective. Here's two very different cob LEDs. You can see the difference if I turn them on. Well, probably can't because of overexposure, but this one here's only got 1, 2, 3, 4, 5, 6, 7, 8 cob LEDs, and I think this one here, 2, 4, 6, yeah, this one here is 16. So they're not even using the same panel unit to unit. And a couple of these that I've taken apart. Here's parts and pieces out of a couple of them. This one here, you can see it had a separate LED and button panel, and only one of them was resistor governed. The other one, they were just relying on the internal resistance of the batteries. This one here also only had one resistor. Another one or two that I took apart did have two, but this one here, they've managed to combine the LEDs and the push button switch all into one board here. But yeah, there you go. They're made as cheaply as possible from apparently whatever supplier they can get. But what'll make this kind of amusing is I've currently got 8 of them lined up here. And there you go, 8 of them shining on the panel, and I'm getting between 15 and 16 volts out of this thing. Well, that's kind of amusing. I mean, that's just 8 of these little guys with cob LEDs powered by AA batteries. And you can see the blue lights on flashing there, indicating that the unit's powered up. I wonder how much of the, I don't know, 120, 150 milliamps this thing puts out is being consumed just by that little circuit there. Let's scale this up just a bit. There is a giant cob LED panel. It's rated, quoties, for 12 volts at 70 watts. In order to tone it down a little bit so it doesn't overheat as quickly, I've got a ballast here rated for 30 watts. So this will put out a maximum of 12 volts plus or minus 0.5 at 2.5 amps, current limited. So let's go ahead and turn on this bad boy, stick it on the panel, and see what it does. Okay. Yeah, that'll blind the neighborhood. Woohoo! Yep. Now we're up to almost 17.5 volts unloaded. So there you go. One cob LED panel from China, powering a cheap solar cell from China, et voila. Wonder if I could connect them together and get the perpetual motion machine. Let's go ahead and unplug that. So there you go. That's about all I can do with this on the bench at the moment. At some point here I need to get a load bank on it, but I prefer to take it into direct sunlight to do that. Now you'll notice we have all these little things that look like they're probably screws, and they have these little caps in them, but I don't think they're in there very good. Yeah, they just pop out, so let's just get those out one at a time. Not even sure if I need to save them, but whatever. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And it looks like I missed one over here. 14. Okay, I think this just pops apart. Yeah, there we go. Nothing too complicated about that. Okay, there's the back side of our panel, and there's the back side of our little circuit with the LED, and it looks like it's just been glued in here with maybe black silicone or something. Well, that should be easy enough to cut out, so let's just try that. Oh, I can pull some of this away, it looks like. Oh, there we go. Yeah, there's like a little, oh, cool. What was that? That's, oh. That was the other lead to the solar panel. I'll need to reconnect that if it's ever going to work again. Now, I'm going to try and cut along the edge of this silicone sealant and see if she pops out. Yeah. There we go. Yeah, this one here is a pretty hefty piece of glass, and I think I've ruined it permanently at this point. Let's go ahead and zoom in on that so we can just see. I've ruined it permanently at this point, so let's just finish pulling it apart for amusement. Okay. Okay, I have borrowed my wife's kitchen scales here. Turn it on, it greets me, it says hi, it's very friendly that way. Okay, we are currently set in grams, so yes, that's good. I want to do this in metric. I'll tear it out just to be sure. And now let's go ahead and put the disassembled panel, just the glass piece with the whatever on it. 243 grams, probably closer to 245 before I started peeling stuff off of it, but close enough. So 243 grams. Now, there's the other unit, not including the power cord. With the plastic frame, it's 436. So yeah, not quite double, but that plastic frame is adding quite a bit of weight and heft there to help support this and protect that glass panel from being broken by casual use. This is in principle similar to how utility scale solar cells work. You have a combination of glass and plastic to make it rigid, but in utility scale cells, instead of using the glass as your substrate and just putting this thin film on the back of it, you usually have a large plastic panel acting as your substrate, and then you bond your cells, your collector bus, and all that fun stuff to it, and then laminate the glass on top of it to protect it from the elements. But in any case, this one here, we have the glass, we have the solar cells on the back. They are aligned in strips, and I started to, when I pulled this silver stuff off, I realized I was fully destroying them, but to give you an idea what fully destroyed means, if I go over the mostly unmolested section here, you can see there's a very distinct gap between each strip. Those strips have been sized to produce about 12 volts between the two bus wires, and they're acting in parallel. Over here where I started to tear it off, then you can actually see the light start to actually come through, and the top layer there has that characteristic orange you think of. But these here are just, again, amorphous silicon solar cells. They're a thin film technology, but they're a very old thin film technology. We're not relying on oriented crystalline structures here. They're just deposited and cut into these strips on the actual glass itself. And realistically, this is just a glorified version of what powers a solar calculator. And it's not efficient at all. This here, well, let's pull up the old metric tape measure and just get an idea. That there, oh, right, just about 10 centimeters, so 100 millimeters. And that there, 305-ish. Harbor Freight also sells a what they call a 25 watt version of this, and I forgot to actually take a picture of the surface area, but it's, you know, about 1, 2, I don't know, maybe 5 or 6 times the size of this thing, so I guess that's fair. And it uses I think longer and wider strips as well in the cut, but yeah, not a very efficient panel overall. It does have one thing in common with utility scale panels though. Even though there's not a lot of plastic material on the back of this, that plastic material is not fireproof. Not even slightly. This is the strips that I tore off of it. You know, it's sealed into that plastic frame with this silicone or whatever that is. But okay, let's just cut ourselves a real small piece of plastic here because I don't want to get this out of control. Let's see what that does when subjected to, you guessed it, the Harbor Freight torch. I really should get these guys to sponsor these things. No, wait a minute, actually this one's Burns-O-Matic. The Harbor Freight one quit a long time ago. That's probably about what you'd expect. Melty. Oh, look at that. Very, very flamey, not really self-extinguishing or anything like that. Yeah. It just burns till it runs out of material. How about that? Lots of that nasty black smoke. But yeah, that gives you an idea what would happen in the worst case. This stuff obviously is not fireproof, and frankly I doubt there's anything good to be said about this frame either. It just looks like maybe an ABS plastic or something along those lines. I mean, it's got some good rigidity to it, so it's fine for that application, but it is most certainly not fireproof. But I guess that's all there is to say about this indoors. Okay, let's do the math on what we just found out there. Our critical data were, first of all, the panel was 243 grams roughly in mass, and the dimensions of this guy were roughly 100 by 305 millimeters, I guess. 100 by 305 gets us what? I know I could do some of this in my head, but I don't want to. 100 by 305, 3.05 E4, 1, 2, 3, 4. So yeah, 30,500 is our total surface area in millimeters. And what is 1 square meter? Well, a square meter is 1,000 times 1,000, so it's 1 million square millimeters. So if I take 30,500 and divide it by 1 million, I get 5. So if I take that, divide by, I get 0.0305. meters squared. Okay, what does that mean in practicality? It means that if I'm getting 1.5 watts per 0.0305 square meters, then if I take 1.5 and divide it by that, I should get, okay, 49.2, let's just say that it about equals 50 watts per square meter. We can use that to calculate our efficiency. Now, have no idea how this device was really rated. Let's assume it was rated like a utility scale panel and they used a standard 1000 watts per square meter incident energy for direct sunlight. So if I take 50 watts per square meter and divide it by 1000, I get 0.05. That is 0.5% efficiency. Yeah, not good at all. For comparison, utility scale panels, let's just write this down so we have it on record. Utility scale panels, typically 15 to 17%. So that's 0.5%. Good panels are typically 15 to 17%, but they're using better materials. This panel here is only using standard amorphous silicon. It's an old technology. It's not super efficient. Also for comparison, if we were to build a 1 meter squared panel out of all this, what would it weigh? Or I should say, since I'm dealing in metric here, what would its mass be?
The metric system is the tool of the devil! My car gets 40 rods to the hog's head, and that's the way I likes it!
Okay, same calculation. I take my 243 and divide it by 0.0305, 243 grams by 0.0305, 7967E3. So 243 grams, let's go ahead and just do this number again, over 0.0305. So 7967 grams for a 1 meter squared panel, or roughly 8 kilograms.
My name is Homer J. Sip. Ow! Son.
Sounded large when I ordered it.
So yeah, that's getting up there. I don't remember off the top of my head what 8 kilograms equals, but I'll bet Google can tell me. Sorry guys, I'm not natively metric, so I'm going to convert it to pounds just so I can get a rough idea what I'm thinking about here. Convert 8 kg to pounds. Roughly 17.6 pounds. And by the time you add framing and whatnot, I'd be looking at roughly 20 pounds or maybe closer to 9 to 10 kilograms of mass if I wanted to get a total of 50 watts out of one of these guys. Not efficient at all. For comparison, here are a pair of utility scale solar panels. This first one is made by a Chinese company called Jinko Solar, although the actual location of manufacturing was Malaysia. The rating is 320 watts, and if you work out the dimensions there towards the lower right, that comes out to just a hair under 2 meters squared. Mass shown at 26.5 kilograms, that comes out to maybe 55 pounds. Moving to the second one, this one was designed by Q Cells. It's a German company, although interestingly, this one was also manufactured in Malaysia. This one here is rated 335 watts. I don't see a surface area conveniently listed on the sticker, but the weight, or mass if you prefer, is 24 kilograms or 52.9 pounds. As you might expect, as you expand these out, it's not like the glass gets thinner and suddenly the panel weighs a lot less. But these here are obviously far more efficient for the amount of power you're trying to get out of them and the amount of mass you have to install to get that power compared to the old technology that is being used by the Harbor Freight panel. Okay, it is a beautiful day on August 31st at roughly just a little before 10:30 a.m. Right now, on the back side of the house, we're just getting ambient light. We'll kind of use that as a baseline reference to see how the panel performs like that, and then when the direct sunlight comes over onto this side in about an hour or so, we can get a little bit more information. And just to give you an idea what sort of day we're looking at here. Partly cloudy, blue skies, and I'm getting some reflected light from those clouds, but otherwise, we're got a pretty good baseline amount of light out here, so let's just see what it's doing. And actually, we can also take a quick look at the setup here. You'll notice we've got these 2 meters. This one here is connected as its ammeter function, and we have a 200 milliamp scale setup right now, so we should be able to get resolution down into the milliamp range here. And then this one here is currently measuring volts, and you'll notice it's flickering around 14 to 15 in the ambient light. Let's just look at those a little closer here. The solar panel is generating enough internal power to at least illuminate its blue light. The clips are connected over here, and then all of the wiring is kind of tied up on that board just to keep it sensible. And then over here is where we'll actually get our metered power. Now here's where we can see something interesting with such low efficiency panels. Normally with utility scale panels, if you were to touch these together, you'd start generating plasma arcs, and that would illustrate why utility scale panels, when there's faults, can catch fire. This one here...
Where's the kaboom? There was supposed to be an earth-shattering kaboom!
Dead short circuit, voltage goes to 0, but you'll notice we're only pushing about 12.2 milliamps across the entire surface area of this panel. It'd probably sit there and do this all day. I don't want to find out if it would, but it's unlikely it would suffer any damage as a result of that. One of the few upsides to low efficiency. I don't think we have enough power to run this motor yet. This motor is rated 6 volts DC. Let's see if we can get a close-up look at it. Yeah, there we go. 6 volts DC. Wonder when this was made. 22nd of September 1988. This came out of an old cassette tape recorder. Most people don't even know what that is anymore, but it's a nice 6 volt DC motor. Doesn't use pulse width modulation drive or anything funky like that, so I can just connect it straight to power, and if there's enough, it will turn. Right now, though, I don't think there is. We'll need direct sunlight in order to make that work. Yeah, it's not even wanting to turn over when I rotate the shaft, and you can see why there. We're down to about 2 volts and 12.4 milliamps being pulled through it. So yeah, we'll have to come back to that one later. But let's disconnect that now and just try one of these little LED lights. Here's a red one. This is one of those generic replacements that you're supposed to be able to use in like taillight assemblies and stuff on a car. But conveniently, there we go. It's also fairly low power, and so even though it's not operating at full brightness, it is operating here. And what are we getting up here? Roughly 6.5 volts, and we're pulling close to 10 milliamps. This is 12 volt rated. You can imagine it would be a lot brighter. And how many LEDs on there? 1, 2, 3, 4. There's 6 surface mount types. But they're operating at least, so that illustrates something. This assembly here, maybe we can do something with that as well. So on these ones, the lead is normally positive in the car. So they wire it that way in the LED also. Hey, there we go. Yep, it came on. Again, we're not super bright there, but we're definitely getting output on it. This one also has 4 of those surface mount LEDs, and then slightly different type here on the end that's supposed to be extra bright. This is like a little H3 halogen replacement, although it's not really as bright as an H3 halogen. More of a curiosity than a useful piece. But yeah, there you go. And this one, we're not pulling, well actually yeah, we're pulling about 10 milliamps, but we're getting a little bit more light off the clouds at the moment, so we're up to about 6.7 volts, and it's still happy. I think we're still about an hour away from direct sunlight overhead. I'm hoping to come back out here when the light's about this far on the table so that I can photograph this half and get sunlight on that half, or maybe over there on the little farther out. But yeah, it's doing what it's supposed to do, so it works. Again, like we discovered looking at the bench characteristics, the efficiency is terrible, but it's running. And just for fun right now, we're looking at 10 milliamps at 6.7 volts. If you do the math on that, what do we get? Alright, it's now actually almost 2 hours later. We are now back out on the porch, and what I've done is I've propped the solar panel up there on the angled cover of the grill so that I'm getting almost perpendicular exposure to the sun. But yeah, still August 31st, but closing in on 12:30 p.m. And that's getting us pretty much our optimal sun exposure and time for this time of year, I guess. Coming down over here, we also see that the voltmeter is reading 22.6 volts right now, roughly. So the panel, when it's unloaded, is running hot. But just for fun, let's see what this thing does if I just short it out. No sparks. Don't really expect them. Again, this panel doesn't have the efficiency to drive an arc here. But yeah, the voltage collapses almost to zero, and it looks like the absolute maximum we can pull out of this right now is just a hair under 150 milliamps. That seems to be typical of solar panels, though the short circuit current is not very high above the full load current. But let's start over with the LEDs we were working with earlier. Here's the red one again. Let's go ahead and connect positive to positive like we had before, and negative to negative, and see if it comes on. And I got a bad connection on my wires, but that's okay. There we go. Well, there you have it. It is red. It is very bright. The voltage is dropping to about 15.8 off the panel, and we're pulling just about 120 milliamps. So let's run the calculations on that real quick. So we're actually drawing a little bit more than our rated 1.5. That's interesting. Now that LED's heating up, we'll get it out of the way. And try the white LED, why not? So there's our white LED once again. We connect plus to plus, we connect minus to minus, and the voltage, which is unloaded hovering around 22.1, drops to, oh wow, 8.3. And we're still pulling about 140 milliamps this time. So looking at that little guy there, yeah, that white LED is shining really nice and bright now. That's about full brightness as we'd expect. Yeah, let's run the calculations again. Now we're pulling about 1.1, 1.2 watts off of that. Third and finally, let's go ahead and check and see what our motor will do. Again, this is a 6-volt nominal motor. I also put a little colors on the shaft there, so hopefully it shows up a little better on camera that's spinning, but it has that little flag there, so let's see if we can pick that up. Minus to minus, plus to plus. And it's really going. In fact, it's spinning a lot faster than it looks like on the side view camera there, but the shutter effect is capturing it for us. What are we pulling this time? We have just a hair under a watt. So there you have it. Our nifty little solar panel up there is indeed capable of putting out its rated 1.5 watts. And while the efficiency is terrible, it is in fact telling the truth about its capabilities. So, way to go, little guy. You did your job today. Okay, just one last thing to check before we wrap this up. We've had this panel now out in the sun for a good long while. So, what temperature is it going to get to? Well, it's looking like around 140 degrees. 155, 160. Or we are in Celsius, 60, 65 Celsius. So yeah, it's not as cool as it could be if it were suspended off this panel, but most of that is just from direct sunlight exposure. It's going to get a lot of heat, stay nice and warm. Well, there you have it, the Harbor Freight solar battery charger. Rated 1.5 watts at 12 volts, slightly exceeds that under best case circumstances. Efficiency is terrible as can be expected for the old technology, and the cost per watt is not great, but for its size and capabilities, it's a great little science experiment, and it's not too pricey. So if you want one, it's probably worth picking up. It won't do a whole lot once you have it, but it's fun for a while. Thank you for joining us for today's presentation. We did not receive any sponsorship or support for this broadcast or for the materials and equipment used. This was solely at our own initiative, and we hope you enjoyed it. Thanks. Please join us again next time, whenever that happens to be. Has anyone seen my phone?